In the process for oxidative coupling of methane, OCM, involving reaction of methane with oxygen under high temperatures, the reactor effluent consists of a mixture of hydrogen, methane, carbon monoxide, carbon dioxide, ethene, and ethane. There is considerable economic incentive to recover ethene from this reactor product. Use of PSA technology for recovery of ethene offers the potential for the development of an energy efficient OCM process. The optimal scheme for implementation of PSA technology requires the use of an adsorbent that is able to selectively adsorb ethene from this product mixture. Specifically, we require an adsorbent for which the selectivity of ethene with respect to carbon dioxide is significantly high. Of the potential adsorbents, activated carbon is perhaps a cost-effective solution, as concluded in this publication. In this process scheme, say using activated carbon, the extract phase containing ethene plus carbon dioxide and ethane can be led to a CO2 removal unit, say using amine absorption, and the recovered ethane mixture can be distilled to produce pure ethene. The bottom's product containing ethane can be used as a purge gas in the countercurrent desorption operation. The raffinate from the adsorption cycle can be recycled to a methanation reactor whose product is then led to the OCM process. For recovery of ethene from the reactor products in the OCM process, we need to have adsorbents that are selective to ethene, especially with respect to CO2. This is the crucial separation that is encountered. Let us screen the adsorbents for ethene CO2 separations by examining the adsorption selectivity as a function of mole fraction of ethene in the bulk gas phase mixture. The most selective adsorbent is Mn2MDOBDC from Jeff Long's group at the University of California in Berkeley. Surprisingly, the second highest selectivity is achieved with activated carbon. The other adsorbents, such as calcium X, 13X zeolite, LTA4A zeolite, and LTA5A zeolite, are selective to CO2 and not to ethene, according to IAST calculations. The same conclusion can also be drawn from a diagram that plots the mole fraction of ethene in the adsorbed phase as a function of mole fraction of ethene in the bulk gas phase. We need adsorbents that are in the top left corner of this diagram. I examine now experimental breakthroughs for two of these adsorbents, activated carbon and LTA5A zeolite, as reported in this paper published in Separation and Purification Technology 2020. The choice of activated carbon is understandable because the IAST calculations show that activated carbon is ethene selective. However, the IAST calculations show that LTA5A zeolite is selective to CO2 over the complete range of feed mixture compositions. I would like to demonstrate that such IAST calculations for 5A zeolite are misleading because the mixture adsorption equilibrium is subject to strong thermodynamic non-idealities that are not captured by the IAST. Using activated carbon as adsorbent, 4 different breakthrough experiments were conducted, and these are reported in this paper cited here. These 4 experiments are with varying proportions of ethene and CO2 in the feed mixture. This is a feed mixture that is richer in ethene, and the ratio of ethene to CO2 in the feed mixture is 3.2. Here the ratio of ethene to CO2 is 1.7, the ratio of 0.85 for ethene to CO2, and the last experiment is for feed mixtures that are richer in CO2 and poorer in C2H4, and the ratio of C2H4 to CO2 is 0.4. The feed mixture consists of ethene, CO2, argon, and nitrogen. The argon breakthroughs are shown here. There's nothing remarkable to note here. And the nitrogen composition is just the remainder of the composition, and it's just an inert. It has little or no effect on the breakthroughs of the other guest molecules. We note that in all cases, the first component to breakthrough is CO2. You can see the breakthroughs of the red circles here. and the last component to break through is C2H4. This implies that C2H4 is the component that is most strongly adsorbed, and the adsorption selectivity of C2H4 to CO2 is larger than unity for all four feed mixture compositions. The breakthroughs with LTA5A zeolite have a strikingly different characteristic. Here I show the experimental breakthroughs for four different feed compositions in which the feed ratios of C2H4 to CO2 is maintained at 3.4, 1.8, 0.9 and 0.75. For feed mixtures that are richer in ethene than CO2, the component that breaks through earlier is C2H4, indicating that the adsorbent LTA5A zeolite is CO2 selective. The situation is quite different for a feed mixture in which the ratio of C2H4 to CO2 in the feed mixture is 0.9. In this case, we see that the breakthroughs of CO2 and C2H4 occur at the same time. This indicates the phenomena of adsorption azeotropy, and the reasons for this azeotrope formation is discussed in the video presentation, Adsorption Azeotropy Explained, that is available for viewing on my YouTube channel. If the feed mixture is richer in CO2 than ethene, we see that the component to break through earlier is CO2, and the component to break through last is C2H4. In other words, we have a situation in which ethene is selectively adsorbed from the feed mixture, provided the feed mixture is lower in composition with respect to ethene as compared to CO2. So we have selectivity reversals. The selectivity reversal phenomena is explained in this video presentation that is available on YouTube. Clearly, the IAST does not anticipate this characteristic, as I shall demonstrate in the subsequent slide. For the breakthrough experiments with LTA5A zeolite as adsorbent, using a feed mixture in which the ratio of C2H4 to CO2 in the feed mixture is 0.75, I compare the breakthrough experiments with breakthrough simulations in which the mixture adsorption equilibrium is determined using the IAST. The breakthrough simulations using the IAST are shown here by the continuous solid lines, blue for ethene and red for CO2. The IAST anticipates that the last component to break through is CO2, whereas in the experiments, the last component to break through is C2H4. So the IAST does not anticipate the selectivity reversal phenomena that is a characteristic of CO2 capture with cation exchange zeolites, as I have explained in several publications. 3 of these are listed here. You may refer to these publications for quantitative appreciation of the phenomena of selectivity reversals and why they occur. I also explained this in my YouTube video, Zeotropic Adsorption Explained, that you can view on my YouTube channel. If we incorporate thermodynamic non-idealities and carry out breakthrough simulations using the real adsorbed solution theory with the fitted Wilson parameters, the breakthrough simulations shown by the continuous red lines and continuous blue lines are in good agreement with experimental data. 2 important conclusions that emerge from these presentations are the following. For recovery of C2H4 from the products of the OCM reactor, we need adsorbents that are selective to ethene, and the crucial selectivity is of ethene with respect to CO2. Activated carbon is a candidate adsorbent. However, the experiments reported by von Zandvoort and others, including myself, and reported in Separation and Purification Technology in 2020, show that LTA5A could also be a candidate adsorbent, provided the feed mixtures are significantly leaner in C2H4 with respect to CO2, as is the case in the OCM reactor products. The breakthrough experiments can be reproduced by the RAST, but not by the IAST. This underscores once more the strong non-idealities that are inherent for CO2 capture with cation exchanged adsorbents.